right, we are starting chapter 11 on sequences, series, induction, and probability. We'll do a little work with sequences and series, and we'll do a little work with induction, mathematical induction. I doubt if we have time to get to the probability, but we can always dream. So we're going to start off with section 11.1, which are sequences and series. Now this is very general. You may remember from your Algebra 2 days that you had arithmetic and geometric series and sequences. Well, now we're just going to kind of think of them in more general terms, so they're not any one specific type. When we think of a sequence, we think of like a progression of elements with some order or pattern. For example, salaries. I have some salaries listed here for a particular job over the 5 years, and as you can see, this is an increasing sequence. The values 22,000 to 25,000 to 28,500 and so on up the line, all the way up to year 5 at 36,000. You can see that then the numbers are getting bigger. So this is a very finite sequence in that we only have 5 terms. And what we normally will do with sequences is that we will list them separated by commas. So let's get to the definition first. Finite and infinite sequence. An infinite sequence is a function. Notice I underline function here because we don't typically think of a sequence as a function. We think of it as just a list of values, but it is a function, and the domain is the set of positive integers. Now the positive integers being 1, 2, 3, 4, 5, and so on. A finite sequence is a function whose domain is the set of the first n positive integers. So like here, I have n equal 5, I have 5 possibilities. And what we would normally do is we'd say, well, if this is our first one here, if our domain is 1, element of the domain is 1, then we would say, oh, f of 1 would be this. But instead of saying f of 1, we use a sub 1 to represent that same notation being 22,000. Oops. A sub 2 being 25,000. A sub 3, A sub 4, A sub 5. So when we would write them out, we would write them out as a list. We would write 22,000. 25,000. You have to be careful when you have 3 zeros like this because they'll think it's one really long number or something. 28,500. 31,000. And I'm going to run out of space as usual. 36,000 being my 5th term. The first term, the second, the first term, the second term, the third term, the fourth term, the 5th term. So a sub 1 is used instead of f of 1. Alright, a sub 2 is used instead of f of 2. For a positive integer n, then the value a sub n is called the general term or the nth term of the sequence. I don't have one listed out here because I don't have a set pattern, other than the fact that the numbers were increasing. And what we normally do is if we can write the general term, we typically list it in here with braces around it, and this symbol right here represents the entire sequence. A sub 1, A sub 2, A sub 3, all the way up A sub n, including and so on and so on and so on, depending if it's infinite or if we have it stopped somewhere. So I'm going to do a couple of examples coming up here, but I kind of want you to get used to the notation. A sub 1, A sub 2, A sub 3, and so on. Write the first 4 terms of the sequence defined by the nth term. Now they've given us the nth term or the general term in both of these, and what we want here are the first 4 terms. So we want b sub 1, we want b sub 2, we want b sub 3, and we want b sub 4. That would be the first 4 terms. So we substitute in 1 in for n, 2 times 1 plus 3, 5. We plug 2 in for n, 2 times 2 plus 3, 7. We plug 3 in for n, 2 times 3 plus 3 is 9. We plug 4 in for n, 2 times 4 plus 3 is 11. And we have the first 4 terms. You can write it like this, or if you prefer, you can write it like this. And those would be the first 4 terms of the sequence defined by that general term. Now over here, and I even made note of it out here so I wouldn't forget to talk about it, but with that negative 1 being raised to a power, you're going to see we're going to have what we call an alternating sequence, in that the signs are going to alternate from negative to positive and so on. And we want the first 4 terms of this one as well. So we want d sub 1, we want d sub 2, we want d sub 3, and we want d sub 4. D sub 1, you would substitute 1 in here, so that's going to give me negative 1 to the first, which is negative 1, times 1 squared, which is 1. So negative 1 times 1 is negative 1. Then I plug 2 in. Well, negative 1 raised to an even power is positive, so this is going to be positive 1 times 2 squared is 4, so that's going to be positive 4. Substitute 3 in. Negative 1 to any odd power is going to be negative 1, so this is negative 1 times 3 squared, which is 9, so negative 1 times 9 is negative 9. And then I plug 4 in, that'll be positive 1 times 4 squared is 16. And as you can see, the signs alternate here. Negative 1, positive 4, negative 9, positive 16, and that would be your first 4 terms. Now, I wanted to also mention here, if your first term was going to be positive, and if you have it written this way, it's going to give you a negative, you can change it so that the first term is positive by putting like a plus 1 here. And that would make the odd number go in and even, and that would give you a positive negative 1 to an even power is positive number. So if you have negative 1 to the n, your first term is going to be negative. If you have negative 1 to the n plus 1, your first term is going to be positive. So that's useful because there are times when we are given a sequence as a list here rather than in terms of the general term like I had been in these two examples, and then we have to write the general term, and that sometimes can be challenging. That's how you handle alternating sequences. And you're going to see alternating sequences again, trust me, in calculus, but probably not until you get into Calc 2. Alright, because a sequence is defined for only positive integers, its graph is discrete. Now discrete set of points. It means that it's not a continuous, it's broken up into individual points and such rather than a curve. So if I was to, for example, this guy right here, a sub n is equal to 2 to the n minus 1. I would start with a sub 1. A sub 1 would be 2 to the first, which is 2, minus 1 is 1. So a sub 1 would be right here. If I was to plug in and find a sub 2, that would be 2 squared, 4 minus 1, which would be 3. So that would be 2, 3. If I was to plug 3 in and find a sub 3, that would be 2 to the third. 8 minus 1 is 7. So that's 4, 5, 6, 7. And I don't think I have it tall enough to do the next one. If I was to plug 4 in, I'd have to be up to 15. Ooh, that's 7. So there's another 7. It'd be way up here somewhere. Probably up here somewhere. You can see it's kind of the point of an exponential curve, partly because this is base is constant here, and the quote variable is in the exponent. Now this is what we're used to seeing when we look at an exponential curve. F of x equals 2x to minus 1. That would look more like this. It would have a, as we know from our work with exponential functions in a previous chapter, it would have a horizontal asymptote, and it would be what, through, if I plug in, let's see, 0, I get, no, hang on. If I plug in 0, I have positive 1. If I plug in negative 1, I have negative a half. Okay, here we go. So it would do something along, if I plug in 1, I'm at, nah, it's up. I can't do arithmetic all of a sudden. If I plug in 0, that's 0. Good Lord Almighty. You can tell it's Monday. I am messing up big time right here. There we go. 1, 2, and then 2, or excuse me. 1, 1. We'll try it again. Jump the gun. 2, 3. Oh, really messed this one up. And it would look something more like this, what we're used to seeing. And it would go on and on forever and ever and ever. And would also approach the horizontal asymptote. I butchered that one. But anyway, there you go. You can see that these points, as compared to these infinite number of points, the difference in the two graphs, although there are similarities, this is a sequence and this is the general term, and this general term looks just like the rule for this function right over here. Alright, we need to do some more examples, so hopefully I'll do a better job with them. So let's look on to the next video.